Hi everyone, welcome back. In this video, we're going to talk about intermolecular forces. So before we talk about intermolecular forces, we need to understand what is temperature exactly. So temperature is the measure of the average kinetic energy of certain particles. So if we imagine solids, so the particles in the solid state are very rigid, and the motion they are undergoing is vibrational motion. And they're packed close together. For liquids, particles have medium kinetic energy, so they have um, some vibrational energy and some rotational energy. And they're not as closely packed as solids. And for gas, we have translational energy. And they're freely flowing in space. So now, the intermolecular forces happen in between molecules, and there are three types that we are going to examine in this video. So the first type is called London dispersion force, and this force is universal to all the molecules. So every single molecule has London dispersion force. So for example, we can look at water. So if we draw the 3D structure diagram for water, we'll have something like this. And London dispersion force is caused by the attraction between the protons in a molecule and the electrons in another molecule. So the protons in this molecule will be attracted to the electrons in another water molecule. So the strength of London dispersion force can be measured using the total number of protons, which should be equal to the total number of electrons in a certain molecule. So in water, we have 2 hydrogen and 1 oxygen. So in total, we would have 2 times 1 plus oxygen, which has an atomic number of 8. So we would have 10. So the London dispersion force will be 10. The second type of intermolecular force is called dipole-dipole force. And this force only applies to polar molecule. So if a molecule that is a nonpolar, it will not have dipole-dipole forces. For example, we can use water again. So as we know, the molecular dipole for water will be in this direction. We will have a temporary dipole on this molecule as shown here. So if we have 2 water molecules arranged like this, one's like this, and one is like this, the 2 molecular dipoles will attract to each other. The positive end will attract to the negative end, so on and so forth. And if we have some nonpolar molecules, for example, carbon dioxide, which is a double bond to carbon. Since this is symmetrical, this is linear, so it will not have a molecular dipole on this molecule, which means it will not have any dipole-dipole force. The last type of intermolecular force that we will examine will be hydrogen bond. And hydrogen bond is the strongest intermolecular force among all these intermolecular forces. So the hydrogen bond will be specifically applying to molecules containing hydrogen bonded to either a nitrogen, oxygen, or fluorine. For example, water again. So if we have water like this, we have a oxygen and hydrogen bond right here. So if we have another water molecule, this hydrogen will be attracted to the oxygen. Why is that? Because the big electronegativity difference between oxygen and hydrogen will draw all the electrons closer to the oxygen than to the hydrogen. So relatively, we would have a strong attraction between the sort of naked hydrogen proton and the central oxygen atom. And as I said, the hydrogen bond will only apply to molecules containing hydrogen bonded to either nitrogen, oxygen, or fluorine. Now, we look at these three forces, and let's go back to the original solid, liquid, and gas visualization right here. So we can clearly see that the reason why some molecules stay as solid in room temperature is because they have high intermolecular forces in between them. And this high intermolecular forces requires higher kinetic energy to overcome the force. So if we add energy to solids, we are essentially adding kinetic energy to them to each individual molecules to a point that these molecules start to overcome the high intermolecular forces, such that they have some relative motion starting right here, some rotational motion. If we add more energy to the system, if we add more kinetic energy to each individual molecule, they will start moving around even faster. They have a higher kinetic energy to overcome the medium intermolecular forces to a point where the intermolecular forces is effectively zero, because they're moving so fast, passing each other. Each individual molecule does not have enough time to interact with other molecules, resulting in a low or theoretically none intermolecular force. By studying the intermolecular forces, we can also predict the melting point and boiling point of certain molecular compounds. So because the process of melting or boiling is essentially saying when can we turn a solid into a liquid and when can we turn a liquid into a gas. So this is essentially asking us how much energy do we need to switch to states. So if a molecule has very high intermolecular forces, it will require a higher energy input to overcome this high intermolecular force, which is essentially results in a high melting point and boiling point. Vice versa, if a molecular compound has a very low intermolecular forces, it will require a low kinetic energy to or energy input to actually overcome the intermolecular forces in between the molecules, which will result in a low melting point and boiling point. So as you can see, by examining the intermolecular forces, we can not only understand what is really happening when we are melting solids and boiling liquids, or vice versa, we are like condensation, and if we are turning liquid into solid, which is freezing. So what's the mechanism behind the process of those? We can also relatively predict what would be a approximation of melting point or boiling point relative in between molecules. For example, if I want to examine the melting point and boiling point of CH4 and CH3OH. So we can first draw the 3D diagram for these two, and if you are having trouble with drawing the diagram, you can check out one of my previous video on Vesper theories. And now we can see that CH4 is a typical tetrahedral shape, which means it will not have any dipole-dipole forces because it's nonpolar, and it will definitely have LDF, the London dispersion force, because that applies to every single molecule. And we can see that the hydrogen atoms in this molecule are not directly attached to any of the ideal atoms that's used for hydrogen bonds, which are nitrogen, oxygen, and fluorine, which means the hydrogen bond is also not present. However, if we look at CH3OH, we will have a completely different shape. So we will have this band shape on the other side, or attached to C, this O right here, this OH group, OH bond right here. So we can see that the bond dipole is something like this, which means all the electrons will be sort of pooling right here, resulting in a molecular dipole in this direction right here. And for LDF, they do have LDF, London dispersion force, because that's universal to all molecules. For dipole-dipole forces, yes, they do have dipole-dipole force because they are polar. And for hydrogen bond, yes, for hydrogen bond, because a hydrogen is bonded to an oxygen right here. Therefore, we can see that CH3OH has a much higher intermolecular forces comparing to CH4, which means theoretically, CH3OH will have a much higher melting point and boiling point than CH4, because CH4's low intermolecular forces result in a low requirement of energy input to overcome those intermolecular forces. Okay, I think that's all for today's video. Thank you very much for watching.